we need to do the coding itself. And systems like that, because they're very optimized, actually they integrate with the routing itself. I'm not going to get into that many details there. So let's look a little bit at this intra-flow network coding, give you some idea. Now, if I'm talking about selecting the nodes that they're going to forward and what rate they're going to forward, the way these systems work, they assume global knowledge. So the source needs to know what are the links and the quality of links in the system. And basically, based on that, it will decide at what rate has each node has to forward, and it will tell each of them what they need to do. And one big component here, for example, is how the nodes exchange information about what is their link quality metric. So, for example, things that can go wrong here is when the nodes start lying about their link metric. And if that doesn't happen correctly, in other words, if the source has incorrect information about the quality of links, what the source will decide obviously will result in something that is incorrect with respect to the node selection and rate assignment. So you're going to have performance degradations. So how can a node, for example, lie about the link metric? And these are very basic problems in general in what is known as Byzantine resilience, which is all this area of how we design systems where people, processes, nodes can lie. You cannot trust what they're saying. So, for example, in the first case, so the nodes, what they do, they measure what is the link quality and with respect to the previous nodes, and what they have to do is tell the other node, for example, node B that I have here with red, he's supposed to tell R, my link quality to the source S, which is the green, it's 0.27. Why? Because the link quality from B to A is 0.3, from A to S is 0.9. Now, if he's not correct, he's going to lie and he's going to say, oh, my link quality is terrible. It's not terrible, it's very good. So he can say 0.9. And what that will result is the fact that that guy would always be preferred. So he attracts traffic. Now, I should mention that in this case, it's actually difficult to prevent completely this attack from happening. The reason is because there is no way I can verify really what's the correct there unless I have some other trusted source of information. Now, this node, the same node B, what actually can do, he can also try to lie about what other nodes said. So when he is trying to lie about what A said that his quality, link qualities with respect to S, or that type of thing I can prevent. Why? For example, just think about maybe digital signatures or encryption. Of course, those will not be scalable, but I'm giving some example of why you can prevent those type of attacks, because you can prevent malicious nodes from modifying information that comes from other nodes. Okay, so data packet forwarding, that's easy to figure out what the attack is. Basically, there is always, if you have a malicious node, he can just drop packets. So this will really focus on the data forwarding component. So what can make it here problematic is an attack is very simple, actually. And also you can see what the effect is going to be. Packets are not going to make it, so the routing doesn't work properly. What is interesting in this aspect is the fact that whatever we know how to deal with this type of attacks from traditional routing, you cannot just apply it here. The reason is because if you think, for example, the most basic technique that we know, which is monitoring, here, whatever it's forwarded is not equal with what was received. So then what am I monitoring? Because they're not going to match. So it's not that trivial to apply. The acknowledgement delivery component is the one that we know the most how to defend against. So just give you some example of what can happen. Remember that this acknowledgement is sent by the receiver or the destination when it could receive all the packets from a generation. However, the systems that I described, none of them use any type of any protection. You know, it's I teach 355 today, and not today, this semester, and I taught it yesterday. I'm going to teach it tomorrow. And students always assume that confidentiality is the most important. For network protocols, actually, authentication is much more important. authentication and integrity. Who sent the packet? Is that the right packet? So for example, just because systems like that have no type of protection, an attacker, which is the red guy over here, he can just randomly send some acknowledgement, or he can just drop the right acknowledgement. So what can happen in this case, which by the way, these are attacks this is an attack that's not always easy to detect, because it's not the type of behavior that it's easily detectable. In the first case, the source will just start sending a new generation because it will assume that the correct nodes received the packets. In the second case, we'll just keep sending the same generation. Even if the poor receiver said, I received the generation that you sent before, please give me the next chunk. I want to watch the movie. Give me the next chunk. And the source will not be aware of that and will keep sending the same information. So in this case, there are things that you can do that we know how to do to deal with Byzantine attackers. The obvious one, you can always flood, right? It's one packet. You don't want to do that in general just because obviously it's going to have a higher overhead. But at least I would say that here we have some idea. Now what I want to focus on is the new part in the design of such systems, which is the coding and decoding. And I have to put some math into here, into the presentation, right? Just to show you that actually coding it's very formally specified, and we can also specify very formally what can go wrong here. So really sending a coding packet, what really means you can actually express it in the form of a multiplication in a particular group, where what the coding packet really represents is going to represent a vector of coefficients, and the coded packet itself is just the combination, the linear combination using the packets from the generation G and the random linear coefficients C1, C2, Cn that were created. So what is really sent over the network is going to be sent C, which is the vector of the coefficients, and E. That was the coded packet. Now, what can go wrong in this context, which may not seem very obvious in the beginning, is that when we're talking about coding, the network coding, coded packets themselves can be used later on by other nodes to further code, to even further improve the performance of the system. So we are used to think about injection as something that is easily preventable. However, in the context of packet coding, such injected packets, which people call polluted coded packets, can create a lot of damage. So a polluted coded packet is basically a packet that will not verify the fact that E, which is the linear combination, was created using the coefficients that are represented in the code, in the packet that is sent. It can be just garbage there. Okay? But if you formally want to express it out, how do you express it? Basically, it's not going to verify this condition. Actually, this is a generic attack against any type of network coding, not only wireless, but it's particularly detrimental in wireless, and I'll explain immediately why. So if you really want to see what happens when such an attack is created, just think about the initial red packet as a packet that is not correct. That packet is going to be further used in coding other packets, so you can end up with a situation, this is a little bit of an extreme case, but you can end up with a situation in which basically the receiver cannot decode anything. So the throughput can be 0. In reality, it's not exactly 0, how I will show you in experiments. In reality, you end up with almost 0. Why is not exactly 0? Because not all packets code. That that rate assignment and forwarding node selection and rate assignment basically selects a set of nodes that will forward. So that's why you may end up having some packets that they're good, and so that's why you don't have exactly 0. Now, in the context of wireless, the reason that this is very problematic is because wireless is a very resource-constrained environment. So you're really using the biggest resource in wireless is bandwidth. So you're wasting all this bandwidth sending incorrect packets. So this is the problem, and it looks like a very simple problem. And when first time people look at it, it's like, I don't understand why this attack is an issue, because it looks like in authentication, I can authenticate all packets. Why is that a problem? So the reality is that it's not as, I don't want to say easy, but it's not really an old problem as people think, because one of the issues that happens is that if you look at the forwarder, so how can you prevent this attack? You really want any intermediate nodes, and I emphasize that you want the intermediate nodes. You don't want this detection to happen at the receiver, because if it happens at the receiver, you already wasted a lot of bandwidth, so the performance of your system is going to be really terrible. You're going to be able to detect this at intermediate nodes. So what you want an intermediate node to be able, when it looks at the packet that it's coded, to be able to say, oh, this comes from the source. And to keep in mind that that coded packet actually can be a coding of other coded packets. So in other words, if you really want to be able even to apply things like, think about digital signatures, what I would say, oh, I have the source signing the packet. You need to have the source to be able, for example, the brute force type of defense will be the source has to sign any possible linear combination. That's not scalable, right? If you don't want to do that, then what you want, if you want to apply cryptography, which is the first thing that will come to your mind, you need an authentication mechanism that has homomorphic properties, right? You need it to transfer, to keep the same property across the coding, which is basically a linear transformation. And that can be a hash, it can be a digital signature. So that's kind of what people thought that it will be a good idea, and they actually went and designed schemes like that. There are actually lots of digital signatures for network coding designed for pollutions that have homomorphic properties, and they do work. And I will show you what type of performance do you get when you start using them in systems. So they're very expensive. There are so many exponentiations in there that your performance goes down to 10%, 20%. I'll show you experiments immediately. Now, there are some other ways what you can do. So some other direction is to look from because network coding came from the information theory community. So another way to look at it is, okay, if I assume that some of the nodes are going to try to pollute, can I add redundancy in the coding itself, such that even if some packets are incorrect, polluted, I can still recover the packets. So that is a method that actually works pretty well. The only thing to keep in mind that when you're doing that, you're actually reducing how much you can improve using network coding over not using network coding, right? Because you're doubling a lot of the information that you're adding when you're coding, and that's where your resilience to attacker is going to come. Also, those particular type of methods work very well, for example, for peer-to-peer systems, but not so much in wireless, because it really constrains, or the where they're limited is how much bandwidth has an attacker available. And the reality is that if the attacker is near the source, it controls all the bandwidth. So that is possible, particularly in a mobile network. And then people also look at network error correction, but those really, they're not designed for adversarial environments. So I promise that I'm going to show you some graphs. This is the first graph that Jink came, when he wanted to work on this, and I say, well, why cryptography is not working? And he came back to me with this graph. This is actually an implementation. It's a simulation, but it's using real data link quality from the RoofNet testbed at MIT. And what you see here with the black, you see the performance of a well-known system that is doing intra-flow network coding, and this is more. And what you see with red is what happens when you are using one of these homomorphic digital signatures to protect against network coding. And what I insist, and is written in green here, is this happens when you have no attacker in the system. Okay, so if this would have been not working, I would have asked you, so what does it mean when we see the red line so close to the y-axis? Is that good? Is that bad?